warm welcome to our final episode of this April 2025 Bite-Sized Corrosion series, during which we've been spotlighting corrosion failures. During this series, we've been exploring corrosion failures from several perspectives. We've looked at some of why they happen, how they happen, where they happen, how can we prevent them happening in the future. And essentially, we've been trying to get to grips with the different kinds of failures we could be experiencing. Some are just encountered during, if I can term it, normal atmospheric conditions. We've done quite a lot of discussion on the high temperature or extreme environment failures that can be preempted. And joining me today to close out our series is Neil Webb, who's very well known to all of us here at Bite-Sized Corrosion. It's so wonderful that Neil is so willing to share the depth of his experience in corrosion with us, and within that, obviously, evaluating corrosion failures. Now, Neil, when we talk about failures, if we talk about something going wrong, we usually want to find out why it went wrong to prevent it happening in the future. I know you have some thoughts on that.
Yeah, well, as you say, failures imply investigation. And failure investigation as a topic actually has probably got to be my favorite subject. I was very privileged to be a student under Professor Paul Robinson many years back, and he did a lot of external consulting work, and he was forever looking at corrosion failures. And he would gather all his postgrad students, all the postgrad students in the department together to have a look at these events. So I got exposed to this whilst I was still studying. It really was fascinating. The most important thing that I think I grasped from that was that one should not jump to conclusions. Don't look at a situation and say, oh, yeah, it's got to be that, and not look further. You need to look beyond the obvious in order to find the root cause. And yesterday, in our last session, we were talking to Dion Slobbert, and he introduced us to some of the investigation work and the concept of root cause analysis. And so I thought, well, today would be a good opportunity to just give a couple of examples of some corrosion investigations that I've been involved in, where we really did have to look beyond the obvious in order to find out the root cause.
Indeed, Neil, I think root cause analysis, unfortunately, has a name that implies impossible to understand, and it tends to get a bit of a bad rap. But the concept of what it is doing is getting to the root cause to figure out why things are going wrong is absolutely crucial. Well, you've inferred that you've got some horror stories to share with us, so let's get going.
One thing to realize is that the root cause of the problem may not be related to the final failure mechanism. Now, that sounds quite contradictory. But one of the examples that I've had was a situation in a hotel and casino complex where they had a central water heating system. So in the machine room, they had these large steel tanks which were filled with hot water. And I can't remember now whether the heaters were in the tank or not. That doesn't matter. And the hot water was then circulated through the hotel through insulated pipes so that guests would get hot water the moment they opened a tap, instead of having to run the hot tap for ages before the cold water dissipates and the hot water arrives. And these tanks were steel, as I said, and they were lined with an epoxy system, which is a little bit dubious because if your epoxy system is not absolutely perfect and you haven't used the correct grade of material, or if you have not done it absolutely 110% in terms of application, we're dealing with the limiting conditions for an epoxy system.
Very high temperature, yes.
Exactly. High temperature immersion, actually. So you can guess what happened. The tanks failed. Well, actually, the tanks didn't fail. The lining failed. And they found pieces of epoxy floating around in the hot water system. That wasn't where I came in. This was the background. So the manufacturers of the tank then said to them, well, yes, we can replace the tanks, but actually we want to propose to you that we upgrade your system whilst we're busy and we'll put in stainless steel tanks. It wouldn't surprise me at all if they didn't price the advantage of the stainless steel such that it covered the cost of everything. But anyway, that's casting aspersions, which I don't want to do. So the client agreed, because obviously stainless steel tanks are going to be better than carbon steel tanks.
Of course.
And so these stainless steel tanks were then installed. And lo and behold, 3 months after installation, they failed.
Which is just like an inference that Dion made yesterday, making a change without considering all the options. And I'm going to go with the fact that they didn't consider all the options of what could have gone wrong. So why did they fail, and what was the cause?
It was very interesting. These tanks were clad. So they had a layer of insulation around the outside and then an outer jacket. And when we stripped off the insulation, we found that the tanks had failed as cracking.
From the outside or from the inside?
From the outside. So everybody then thought, well, good grief, how on earth can this happen? Because we use stainless steel in domestic water situations all the time. Granted, it's mostly ferritic stainless, our cutlery and so on. But austenitic stainless steels, the 300 series, can handle a certain amount of chloride and temperature, and provided you don't exceed the operating parameters, you've got a safe system. Well, anyway, so this had obviously exceeded it. We had the stress in that these tanks had been cold rolled and then welded, and we had the temperature, they were hot, and we had the chlorides. And the question was, where on earth did these chlorides come from? So the corrosion had occurred from the outside in. And
so it wasn't the chloride in the water from the municipality.
The water. Exactly. Okay. But then the question came is, how on earth did the insulation of the tanks get wet? And this hot, wet poultice on the outside was the final failure mechanism. The question, as I said, was how come that it was wet? Was it a leaking valve? Was it water that had been spilt onto the vessels from some adjacent equipment? Was it them washing down the plant room or what? And the challenge was that this location where the corrosion had occurred did not align with any external source of water. So we climbed into this tank, took the manhole cover off, climbed into the tank, and lo and behold, we had internal bacterial corrosion, which had occurred at a porous weld. So the bacteria had settled at a point on this weld, made a wormhole through the stainless steel shell, and it then leaked water into the insulation. The insulation itself was not glass fiber, which it possibly should have been. It was a mineral wool.
So it absorbed the water and sat there, didn't it?
Absorbed the water and it sat there. And not only that, but this mineral wool was a source, what do you call it, a potent source of soluble chlorides. So the fresh water from the water system soaked into the mineral wool, extracted the chlorides, and then sat on the outside of this tank, which was under stress, and we had this stress corrosion cracking. And that took 3 months. It was quite staggering, actually.
That's incredible, because if all of the conditions resulting in the stress corrosion cracking hadn't been there, that SRB culture would have carried on happily chewing through the steel and pouring water out of the tank. And because the system's effectively an open system, they probably would have never picked it up.
Yeah, possibly.
Goodness gracious me. So really the fault was in the bacteria, but it looked like stress corrosion cracking because that's what was the failure.
Correct.
I suppose that's really why you do need to take your magnifying glass and have a deep look at these examples. Well, SRB are always, so that's sulphate-reducing bacteria for anyone who may not understand, and I apologize for using the acronym as so glibly, but those little bugs are often blamed for lots of things, but they're also often not easily encountered. And I know we had a very interesting discussion with Dr. Reza Javahadachi a while ago on bite-sized corrosion, specifically looking at SRB. But now you've whetted my appetite, so to speak, Neil. Do you have any other horror stories that you'd like to share?
Well, my other horror story is somewhat similar, and it's also a little bit amusing. I suppose it wasn't amusing for the people concerned, but looking at it from the outside, it has a funny side. And that is that stainless steels are quite susceptible to bacterial corrosion at welds. So if the welds had not been pickled and passivated, or if they were slightly porous or whatever, and you've got bacterial activity in a system, the bacteria just seem to love getting into that situation and creating a wormhole. It's a very, very small wormhole. The other example that I wanted to share was a situation where a reverse osmosis plant on a remote island in the Indian Ocean was suffering, I mean, suffering in inverted commas, from stray currents. So that was the description given. The people responsible for supplying the plant had contacted us and said, well, you guys know about stray currents. Can you help? We've got this plant. It's out there in the middle of the ocean on a little island. It's the sole source of drinking water. And the operator is getting shocks from this equipment.
That's
Can you
a
go
little
to
dire.
this? So I packed a crate of test equipment, every conceivable piece of electrical investigation equipment that I could think of, to fly across to the Seychelles. And as I was leaving, something in the back of my mind said, take some bacterial kits because you're dealing with the water system. We just happened to have done a significant bacterial analysis project, and we had a bunch of culture tubes left over. So I threw them into the box. Anyway, so flew across to the Seychelles, got there, flew from the main island to this little island, which was accessible either by a little boat or a little plane once a week. And got there and went to go and have a look at this plant. And the plant was a fairly open plan. And lo and behold, the operator, in true island fashion, was barefoot, shorts. I think he had a vest on, working on this plant, standing in water. And whenever he touched this piece of apparatus, he got a shock. And it was leaking. So obviously it was stray currents. Anyway, I dug out my crate of instruments and went ferreting around. And I discovered that the cause of the stray currents, so to speak, was that their diesel generator set on the island from which they drew all their power was slightly out of balance, for want of a better word. And they had not earthed the star point of the generator. So if anybody out there who knows about three-phase systems knows that you should create an earth using the star point in order to balance your supplies. So the stray current was about a 10-volt AC steady state voltage on this plant, which of course, when you hold onto a piece of conductive steel and you're standing in water, is quite
You
a
will
kick.
get a little bit of a shock, yes.
Yeah. And we talk about AC hazards on pipelines and so on. Well, this was a pretty good example of a steady state AC situation. So that explained the shock, but did not explain the corrosion. And the situation was quite easy to resolve. In the electrical side, they put an earth spike in the generator room and an earth spike in the reverse osmosis room, and the shock went away. And we still were faced with this corroding
Still got water flowing,
component
yes.
of the plant. And the section that was corroding was a stainless steel tube that collected all the reject water from the reverse osmosis process. So the water that was pumped into it was drawn from an aquifer. So it had a lot of organic material in it in terms of organic acids, decayed plant material, and so on, and a fair amount of chlorides, as you can imagine. And this was then pumped through the RO plant. And this particular little component then received the reject water, which was rejected by the membrane. And the problem was that the flow rate in this particular component was very, very low. So there we had all the components for our bacterial corrosion again. We had anaerobic conditions because of the reverse osmosis membrane. We had water, which had salts in it, and it had organic acids in it as a source of food. And these little bugs said, hey, this is cool. And they just drilled little holes through this believe it or not, 316 stainless steel component. And again, they all occurred on welds. And I've still got that particular little component sitting in my war room somewhere. And it was then when we went back and challenged the manufacturers with this, they said, oops, well, sorry, but actually, if we'd known that there was that around, we would have done something different. And what they landed up doing was actually then using, I can't remember, they either used a 904L tube or they used a fiberglass tube. Can't remember which one they eventually decided on was the right way to go. And that sorted out that one.
Well, if you want to avoid corrosion, don't use steel.
Yeah. So there I was now, having sorted out these two problems on day one. I was now stranded for a week on a remote island in the Seychelles.
Well, there are worse places in the world to be stranded.
The dive instructor happened to be a South African, so I made friends with him and spent the rest of the week diving.
I think, Neil, that your stories have just highlighted for us something that possibly is a really useful take-home, is that if there's water involved, never ignore the possibility that there could be microbial action. And the sulphate-reducing bacteria in particular, the little portable culture kits are available relatively easily and certainly respond very quickly. It takes a few days to get an answer and are fairly accurate. And I think that's something that is simple and easy and can rule out, well, it may not rule out that the bacteria are involved, but at least it can remove that as one of the key areas of consideration.
The examples show something that I've gathered over the years in a qualitative fashion. I haven't documented it as such, but whenever you've got a recirculating water system and it gets contamination, any kind of contamination. So a similar situation happened at one of the ammunition manufacturers in days gone by, where the recirculating cooling system for their presses, they had an ammonia leak in a chiller, and this ammonia got into the recirculating system together with some oil. The next thing, bang, they had bacterial corrosion left, right, and center. And the only thing you can do in that situation is that, A, you've got to flush it. B, you've got to get rid of the poultices that form, the scale and everything else. And then you've got to control the bacteria. So it's a challenging situation.
And I think something that we haven't addressed at all in this series, or even perhaps in our Bite-Sized Corrosion series, is the use of additives to recirculating waters, which can deal with excessive oxygen, as in oxygen scavengers, or as in some form of biocide to reduce or restrict the sulphate-reducing bacteria and so on. And I think that's also sometimes a solution. You might not be able to get back to that virgin clean scenario, but there are ways to manage it going forward if it becomes a recurring problem. And I think one of the challenges with corrosion in general is that once you've got corrosion started, it's very difficult to get rid of it completely without a complete rebuild. Your comment about the welds, any repair, those are all sites where the original steel has now been disturbed in one form or another. And becomes a little more susceptible to damage.
Well, you'll remember the investigation that we were involved in together at the hotel in Rosebank, where the firewater system started leaking. And when we went to go and have a look at this firewater system, there was salt crawling out from every screwed joint. And we asked the guy, well, what is going on here? They said, no, they don't know. They don't know what's going on. So we said, well, what is this? No, it's an ordinary firewater system, but we were not allowed to put in a firewater tank, header tank. So we used the swimming pool And guess what? The hotel management changed the operation of the swimming pool to a saline system. So the firewater system landed up getting charged with saline swimming pool water.
Faulty water. Yeah. And I think, again, that goes back to the change management. But when you're thinking about your swimming pool and how to clean it, and you just change the mechanism because of usually cost or ease or both, and you don't realize the additional ramifications because we don't necessarily think about particularly about our safety mechanisms. They're so back of mind that we're not thinking, oh yes, and the pool water is also used as part of the fire system. We just are dealing with the pool as the guests need to see a lovely sparkling pool.
Yeah,
And
yeah.
I think that yesterday's comment about watching the change management process applies across the board. And the implications from a corrosion perspective can be very unintended and unexpected. So, yes, well, Neil, thank you. I think this has been an interesting discussion, and in many ways, I think we've asked more questions than we've answered. But I think as our takeaway, if we're taking away the concept that if we're wanting to change anything, think about what could happen downstream and upstream because of what we're doing. And also that when we're looking at a scenario where there is a failure, is to not go in with the preconceived notion of what has caused the problem, because that might, as you indicated earlier, have caused the actual final problem, but it might not have been initiated by that. And sometimes that takes a little bit of open-mindedness and awareness of what other reactions could have been occurring to make sure that we don't incorrectly penalize something, because the difficulty with that is that we can keep getting the same mistake. So if we keep blaming the water, and so we clean the system out and recharge it and so on, and we get the same problem, well, if you're doing the same thing, don't expect a different outcome. And I think that's also quite important.
That example of Dion's yesterday with the
Yes, the
with
boiler
the
tubes.
interchange.
Yeah.
Yeah, keep on doing the same thing, and don't be surprised if you get the same results.
Indeed. And I think just to close off with a little sort of summary that if we do take what we've learned over the last couple of sessions, we will be in a better position not to let corrosion failures make fools out of us. Now, this really does bring us to the end of our series on corrosion failures, and I do hope that you've enjoyed it. Thank you so much.